Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore the most important IEC standards for electrical engineers. Our focus will be on design, safety, reliability, and global compliance. Over the next few slides, we'll cover key standards that help ensure our work meets international requirements and best practices. Let's get started. Let's talk about the purpose of IEC standards. IEC standards serve as a common engineering language that helps ensure safety, reliability, and compatibility of electrical systems across the globe. Think of it as a universal set of rules that everyone in the industry understands and follows. For example, if a transformer is designed according to IEC 60076, it can be tested and certified anywhere in the world without needing to redesign it. This consistency simplifies international trade and guarantees that products meet the same high standards no matter where they are made or used. Overall, IEC standards are fundamental in creating a seamless and safe electrical infrastructure worldwide, which ties into our broader theme of ensuring quality and interoperability in electrical engineering. Let's take a closer look at IEC 60364, which focuses on low-voltage installations. This standard is crucial because it sets the rules for designing and verifying wiring systems, earthing, and protection measures to ensure safety and reliability. One of the key points is understanding how to calculate the current in a circuit. The formula I equals P square root 3 times V times PF helps us determine the current, where I is the current, P is the power in watts, V is the voltage, and PF is the power factor. For example, if we have a 75 kW load operating at 400 volts, with a typical power factor, the current would be approximately 127 amperes. This kind of calculation is essential for properly sizing conductors and protective devices, ensuring the system operates safely and efficiently. By following these guidelines, we make sure our electrical installations are both safe for users and compliant with international standards, which is a key part of the overall theme of safe and reliable electrical design. Let's take a closer look at IEC 60038, which defines standard voltages used worldwide. These standards are essential because they help harmonize electrical systems across different countries, making equipment compatible and safe to use globally. One key point is the distinction between AC and DC voltages, both of which are specified within this standard. Now, an important formula to remember is VL equals the square root of 3 times VP. This is crucial for understanding three-phase power systems, which are common in industrial and large-scale electrical setups. For example, if you have a single-phase voltage of 230 volts, the corresponding three-phase voltage is approximately 400 volts. This conversion is vital when designing or troubleshooting electrical systems to ensure compatibility and safety. Overall, understanding these standard voltages and their relationships helps us create more efficient and reliable electrical infrastructure worldwide. Let's take a closer look at IEC 60909 and how it helps us determine short-circuit currents. This standard provides us with reliable methods to calculate both symmetrical and asymmetrical fault currents, which are essential for designing and protecting electrical systems. One of the key formulas you'll encounter is IK equals C times UN divided by the square root of 3 times ZTH. This formula helps us estimate the short-circuit current at a given point in the system. For example, if we have a voltage of 400 volts and an impedance of 0.005 ohms, plugging these into the formula gives us a short-circuit current of approximately 50 kiloamperes. Understanding these calculations is crucial because they influence the selection of protective devices and ensure system safety. Remember, IEC 60909 is a fundamental part of ensuring our electrical systems can withstand and safely disconnect during faults, aligning with our overall goal of reliable and safe electrical design. Let's take a closer look at IEC 60076, which is the standard for power transformers. This standard covers important aspects such as ratings, cooling methods, vector groups, and testing procedures. Understanding these parameters is crucial for selecting and maintaining reliable transformers. For example, when calculating the apparent power, or kVA, we use the formula S equals the square root of 3 times the voltage times the current, divided by 1,000 to convert to kilovolt amperes. So, if we have a transformer operating at 400 volts and carrying 300 amps, the apparent power would be 208 kilovolt amperes. This example helps us see how the formula applies in real-world scenarios, emphasizing the importance of proper ratings and testing to ensure safety and efficiency in power systems. Let's take a closer look at the IEC standards related to switchgear. First, IEC 62271 covers high-voltage equipment like breakers and disconnectors, which are essential for managing power at very high voltages. On the other hand, IEC 60947 focuses on low-voltage switchgear such as MCCBs, ACBs, and relays, which are critical for protecting and controlling circuits in lower voltage systems. An important point to remember is how to select the appropriate breaker based on short-circuit current levels. For example, if the available short-circuit current, ISC, is 25 killamps, then the breaker you choose should have an ultimate breaking capacity, IQ, of at least 36 killamps. This ensures the breaker can handle fault conditions safely and reliably. Connecting this to our overall theme, understanding these standards and selection criteria is crucial for designing a safe and robust electrical system that complies with international guidelines. Let's take a closer look at some important standards related to protection and safety. First, IEC 60529, which defines the IP code for enclosure sealing. This helps us understand how well electrical enclosures are protected against dust, water, and other environmental factors. It's a key point in ensuring equipment durability and safety. Next, IEC 60479 sets limits on touch and step voltages. This is crucial because it specifies the maximum voltage levels that can be safely encountered without risk of harm. When we talk about current, remember the formula I equals V divided by R. That's the basic electrical relationship. For safety, the current should be kept at or below 50 milliamps, which is generally considered the threshold for safe exposure. Connecting these points, both standards work together to enhance safety, whether it's protecting equipment from environmental hazards or ensuring human safety from electrical contact. Keeping these standards in mind helps us design and operate safer electrical systems overall. Let's take a closer look at some key standards that help us ensure system stability and safety. First, IEC 61000 focuses on electromagnetic compatibility, or EMC. This standard is all about making sure our systems don't interfere with other devices, which is crucial for reliable operation. On the other hand, IEC 61508 is about functional safety, setting the framework for how safe our systems need to be. It introduces the concept of SIL, or safety integrity level, which quantifies the level of risk reduction. For example, achieving SIL3 means we can reduce the risk by 99.9%, significantly increasing safety and reliability. These standards are vital because they help us design systems that are not only stable, but also safe under various conditions, tying directly into the overall goal of creating dependable, resilient solutions. Let's wrap up with a quick summary of the key points we've covered. IEC standards are crucial because they ensure that electrical systems are safe, efficient, and capable of working seamlessly together. For example, IEC 60364 deals with wiring practices, making sure our electrical installations are reliable. IEC 60038 focuses on voltage levels, which are fundamental to system stability. When it comes to faults, IEC 60909 provides guidelines to handle those situations safely. Transformers are covered under IEC 60076, which ensures their proper design and operation. Switchgear standards like IEC 62271 and IEC 60947 help us manage switching devices safely and effectively. Safety in enclosures and protection is addressed by IEC 60529 and 60479, highlighting the importance of safeguarding both people and equipment. Lastly, IEC 61000 and IEC 61508 focus on electromagnetic compatibility and functional safety, which are especially critical in our increasingly interconnected world. Overall, these standards form the backbone of reliable and safe electrical systems, tying everything together in our effort to create safer, smarter, and more efficient electrical infrastructure.